The first technique we'll look at then is partial fractions. So if you want to decompose a fraction, you're trying to integrate this some function x on some other function x. So we're dealing with polynomials. Now, polynomials on polynomials. Now, if the degree of the numerator is greater than or equal to the degree of the divisor, first thing you do is do a polynomial division. Okay. So once you've done that, you'll end up with a fraction where the degree of the numerator is less than the degree of the denominator. So you try and factorise the denominator. Now, depending on what your factors are, for every linear factor that you've got, you set up a fraction a on that factor, x minus a. If you have multiple linear factors, then you would write one for every power. Okay, so if it was cubed, you write a on x minus a plus b on x minus a squared, c on x minus a cubed. So one for every power. And then the only other factor you could have, because remember all polynomials can be factorised down to be a combination of linear and quadratic. So the only other thing you might have is a quadratic factor. And so if you have a quadratic factor, you set up a fraction with a linear factor on the top, so degree of one less. Ax plus b on ax squared plus bx plus c. So let's just look at some. We'll start with some easy ones, I guess. So x squared on x plus 1, well, the degree of the numerators are greater than the degree of the denominator. So first thing we do is a polynomial division. And if you're not sure by looking at it, then okay, we'll go and do the actual division. X and x squared goes x. X into minus x is minus 1, remainder of 1. So we know we can rewrite that as x minus 1 plus 1 on x plus 1. Now the x and the minus 1 we can integrate quite easily, and then we just have to look at the other fraction and see what it is. And that one would be a, it's a log function, isn't it? So we'll get half x squared minus x plus the log of x plus 1. Plus, of course, a constant. So never forget, polynomial division first. Look for first. So let's now just look at integrals that we don't have that polynomial division. So I've got 3 on x squared minus x. Well, we said that when we got something like this, we'll factorise the denominator. So this is x outside of x minus 1. So we set it up. So just over to the right-hand side, I said, well, I'm going to decompose this algebraic fraction into the question. So we're so used to having algebraic fractions where it says, oh, this plus this, go and combine it into one fraction. So this is decomposing it. It's going back the other way. So what we're saying is, well, we would have had two fractions. Something on x plus something on x minus 1. We would have added them together and ended up with this 3 on x, x minus 1. So the question is, what are a and b? That's what we have to find. Well, if I just multiply everything by x, x minus 1, I get myself a little equality to solve. And by clever choice of pronumerals, I can solve this quite easily to find a and b. Like I could pick any number I like. It'd be silly to pick, say, 10. Not going to help me. I want to try and at least make one of the letters disappear. So if I make x equals 0, I haven't got any b's. So straight away I get, oh, negative a is 3, I know a is negative 3. And now if I make x equal to 1, the a disappears, and I get b is equal to 3. So we now know that this came from minus 3 on x plus 3 on x minus 1. Now the beauty of this sort of question is, whenever we have a linear factor in the bottom, it must have come from a log function. There's no other choice, because derivative on function. So I know both of these will end up being logs. So I've got minus 3 log x plus 3 log x minus 1. In this case, because the coefficients are both 3, I'll probably combine that into one log there. So 3 log x minus 1 over x. If those weren't the same, I probably wouldn't worry about it. Depends what I'm going to do with the answer, I suppose. So there's no polynomial division to be done here. If I factorise, or does that factorise? Multiply together to give negative 10, add to give negative 3. Yeah, it does, doesn't it? So we can factorise that to be x minus 5, x plus 2. So again, we'll set it up. And exactly the same. Let's clever choice of pronumerals. So I'll make x equal negative 2. That'll make the a disappear. I get b is minus 3/7. 5 will make the b disappear. We get a as 10/7. Remember this one, there's something to substitute in the right hand side as well. Be careful with that. Remember, you're substituting into all the x's. Okay. 10/7. Again, they're linear factors on the bottom, so I know they're going to be logs when I integrate. So I have 10/7 the log of x minus 5 minus 3/7 the log of x plus 2, plus of course a constant. And I've just left it there. I mean, I could have said common factor of a 7th, brought the 10 in as a power there, brought the 3 in as a power. I mean, you could combine it all into one if you really wanted to. I just don't really want to. Okay. dx over x cubed plus x. Okay, let's factorise it. Oh, I got a quadratic factor this time. So when I set this one up, I'll have a over x, but the other one's going to be bx plus c. So order 1 less. Order 1 less than a quadratic is a linear. And again, multiply out. Oh, okay, what shall I use? Well, I might do x equals 0 first of all, because that'll get rid of the bx plus c. And I can work out a. All right. Oh, what shall I try now? Well, who said I had to use real numbers? Okay, if I make x equal to I, then the a will disappear. Because x squared plus 1, sub in I, that's 0. So I get minus b plus ci is equal to 1. Oh, the real part must equal the real part, the imaginary part must equal the imaginary part. So b equals -1, c equals 0. I mean, there's nothing says you can't use imaginary numbers. Other ideas you could use there, I could have said, let's look at the coefficient of x squared. On the left-hand side, the coefficient of x squared would have been a plus b. On the right-hand side, there is no x squared. So a plus b must equal 0. We just worked out a was 1, so b is -1. I could have said, let's have a look at the x's. And you get a similar sort of thing. So you can combine different methods. All right, back to our integral though. 1 on x, well we know that's going to be a log. X on x squared plus 1. Well that's going to be a log as well. The degree is 1 less than the bottom. So I get the log of x minus a half the log of x squared plus 1. You get a lot of logs in these questions. X dx on x plus 1 squared, x squared plus 1. Okay, I'm going to have a fraction for each of those linear factors to the power of 2. So I've got a on x plus 1, but also b on x plus 1 squared. Then x squared plus 1, I'll have a linear factor on top, cx plus d. Multiply out, and this is the little thing I've got to solve. What shall I use first? X equals -1's looking good. Yep. So x equals -1. I get b is -1/2. I could do x equals I. All right. So that gets me c and d. I still haven't worked out a. Well, now that I know b, I know c, I know d, well, the easiest number to substitute in is 0. So let's sub in 0. I get 2a plus b plus d is 0. But I know what b and d are, so from all that I can work out that a is 0. So my fraction becomes -1 on 2x plus 1 squared plus a half on x squared plus 1. We haven't got log functions this time. We've got x plus 1 to the -2. There's that. Remember I said it's a handy integral to remember, the 1 on u squared. That's basically what we got there. And x squared plus 1, that's inverse trig. So just to highlight it, I've changed it to the power of -2 there. Add 1 to the power over the power, and the second one becomes inverse tan x. So a half of 1 on x plus 1 plus inverse tan of x. Well, there is an alternative way for finding those constants. Okay. So when the denominator is just a product of linear factors, it's known as the cover-up method. To find a, substitute little a into the function. But look at the function you're substituting into. It's like you've covered up the factor x minus a. So you substitute a into it. So then to find b, I'll cover up x minus b and substitute b into it. To find c, I'll cover up x minus c and substitute c into it. Right? So, and so on for all the constants I want to find. So back to our first example there. So what I could have done, to find a, I could have covered up the x and substitute 0 in, I get negative 3. So a is negative 3. Now I want b, so I could have covered up the x minus 1, but substitute 1 into it. 3 over 1, that's 3. There's our answer. What about the next one we looked at? Same idea. I'll cover up the x minus 5, sub 5 into it, and I get 10 over 7. To work out the b, I'll cover up the x plus 2, sub negative 2 into it, because remember it's x minus the value. So substitute negative 2 into it, and you get minus 3/7. Well, everyone says cover up method you can only use for linear factors. I'm going to call them out on that one because, again, why? We know complex numbers. So you could apply this to quadratic factors as well. A over x, cover up the x, we get the 1. Now, the x squared plus 1, if I cover it up, what do I substitute in? Right? You're basically making the factor equal to 0. So if I cover it up, I get bi plus c is equal to 1 on I. Well, 1 on I is, of course, negative I. So b is negative 1, c is 0. All right, let's try it with this one then. To work out a, fair enough. Cover it up, I'll sub in 1. There's a. Now, 4x squared plus 1. What would make that equal to 0? I on 2. So substitute I on 2, I get bi on 2 plus c is equal to I on 2 squared plus 4 lots of I on 2 over I on 2 minus 1. Okay, it might start getting a little bit complicated here. There's a little manipulation, but hey, eventually...
Oh my god.
And that's why it's good to have a combination of ideas to use. Because what I'm saying to you, the idea works. In this case, it might not be the best idea. What about multiple factors? Just a little bit more work here. So this one. To work out a, cover up, not a problem. To work out, what do I cover up? The x, they're both, you go with the higher power. So this will work out c. Cover it up and we'll get c. Then we're just going to have to use a substitution to work out the other one. So I'll let x equals 0, always the easiest number to substitute in. And we end up with, there we are, b equals 2. So the idea does translate to quadratic factors, multiple factors. It's just most commonly used for linear factors, I guess. Okay, then we had this one, because x plus 1 squared is the higher number. So it's the b we cover up. Okay, now we look at the cx plus d, cover that one up, and we'll substitute in I. And so equating real and imaginary. And now to work out a, it's the only one left, so let's use a little bit of algebra. A plus b plus d is 0. A turns out to be 0. What about if you have a quadratic denominator that can't be factorised? So say we had something like this. Well, a is going to be easy enough to work out, so let's do that. X squared plus 4x plus 5. What would make that equal to 0? Oh, it doesn't factorise. Complete the square and find an appropriate substitution.
We're going to use that. Okay.
I'll let x equal minus 2 plus I. As I say, probably not the best idea, but just to show the idea works, it does carry through. So if we cover up, we get minus 2 plus IB plus C over, equals 2 or minus 2 plus. Eventually we get B is negative 1, minus 2B plus C is negative 1, so C is negative 3. It will work. Again, probably not the best technique to use for that question, but it would work. Alright, so in our Patel 2G, the odds, and our Cambridge 2C.